Welcome, guys. Welcome to Upskill Club, Season 3, Episode 4, focusing on system design. Today we have, I guess, one more new guy, Abhishek. Hi, welcome to Upskill Club. Um,
So,
an enormous amount of audience, as usual, with Antriksh in the audience. So, for Abhishek's context, I'll tell you what we do here, Abhishek. What we do is we talk about a problem. In this season, so normally we go season by season. In the first season, we focused on microservices. Second season, we focus on the base of distributed system. In the third season, we are focusing on system design. And I have already planned the fourth season. I'll see you soon in the fourth season. See,
amazing.
so we do this. We discuss a problem statement in a detail and we just give our thoughts. And we try to create correlation with the technology that we already use in our day-to-day job. Okay. So since in this season we have already discussed a rate limiter and how it is configured at UC. We have discussed consistent hashing. We have discussed how to create a key value store and how in any distributed system and how consistent hashing is very predominantly used. Today we'll discuss. How do you generate a unique ID in a distributed system. Okay, Harsh is also here. Hi, Harsh. Harsh, can you hear us?
Yes, Anupam.
Okay, cool, guys. We were just about to start. Abhishek has joined us recently, and it will be good if you can also wash your face and turn on your video soon. So let me get started. So we have all used unique IDs, right? It is part and parcel of our job. What is the first thought which comes to your mind per se when you think about any unique ID? Antrix can take a start. And Antrix, what is your personal exposure to unique IDs?
So unique IDs in general, so DBs may
Your
yes.
personal exposure, not in terms of information. We all know they exist.
Acha.
What has been your personal exposure?
So for me, unique IDs was something that I recently used. So basically for performance logging, as we know, we are working on performance logging for front end. So basically on that, I need to match every metric on a particular session. So it's start transaction and end transaction. So to match that, I had used unique ID and I generated that so that a metric gets mapped on its starting time and ending time correctly. So for me, that has been one of the exposures for unique ID.
Okay. What about you, Abhishek? In what shape and capacity do you remember?
So unique identifiers for me have been pretty basic. I mean, I just know that we use it in MySQL Mongo, and it identifies one database entry, and it has
Fair
to be
enough.
in that database.
Okay, that's fair enough. What about you, Harsh?
I think like general, I think that unique IDs over a system should not like conflict with each other. Like
No, no,
transaction
we're
ID
not
should
asking
be
what is
unique
unique ID. RT. We're not asking what is unique ID.
and
We're asking.
things like that.
I guess, I guess your internet is breaking, or is it mine?
Nice. It's Harsh's internet.
Okay. Harsh, can you hear us?
Anupam, just give me 1 minute. I'll just switch to different network. 1 minute.
No worries. We'll wait. I'll pause the recording also.
Yes,
Well,
Anupam.
Harsh, the question is actually what is your exposure to unique ID and what shape and form you have seen unique IDs in action. One is
Got it.
very trivial that we all have seen, which is Mongo, correct?
Yes.
One
I,
of the use case that Antrish mentioned was unique IDs for events that we send from front end.
yes. Even I have mostly related to that only exposure with the DB unique ID that is generated.
Cool. So today's session is about unique IDs. Obviously, that is an obvious giveaway. So what we'll do is now the question is how do they get generated in principle, and what are the challenges are there for a distributed system? Obviously, generating on one single laptop with an auto increment is fine. That is what we have learned, correct? But what about distributed system? That is what we'll explore today, one by one. So some of the characteristics for a unique IDs are it must be unique, correct? And it must be sortable also. Remember, there has to be some conscious thought to it so that we can sort it out and make some sense from the ID. That is first. One of the constraints that we can think of, it should be numeric only. Numeric adds the most value. Correct. Mongo says otherwise, but that is my opinion. It must be it must be numeric. Let's just take that as a constraint per se. Then and it should increment by some delta. Correct. It should. I'll not say it should increment by one at every next tick. We call let's call it as tick. But it should increment by something. So it is incremental in nature. And a simple example is ID generated in the evening should be bigger than ID generated in the morning of the same day. Something as simple as that. Yeah. It has there has to be a limit. It's not like you can just go merry-go-round and just create in the name of creating unique IDs. You take good amount of space. So there has to be limit. For our discussion, let's say it has to be fit in 64 bits. Fair enough. And then the system has to have some speed, because it's just not that you can create one ID at one single tick. There can be in decent amount of ticks. Imagine for somebody sending posts at Twitter scale, how many posts that they get at exact same timestamp. Correct. So it has to be some speed to it. So these are the constraints that we'll think about in our discussion, which is it has to be unique, it has to be sortable, it should be preferably a numeric key. It should increase by some amount. It should have some limit to its size, and the entire system should have some speed. Okay, those are the things that we discuss about in next set of discussion. There are four things that we discuss. Go.
Numeric, numeric you are saying only because of sortable wala feature, या फिर is there?
Sortable, yes. It becomes harder, so your algorithm will become harder. Yes, you can do it. Just
But
because it
why,
will become harder.
why does it need to be sortable? Matlab, why does unique IDs need to be sortable? Are we talking about auto increment IDs or unique IDs?
Unique and auto increment in a large scale system.
Okay, got
In a
it.
large scale system, it should not only that. Those are the constraints that we are saying, right? So we are saying these are the constraints that we'll talk about. Okay, it
Okay,
is
okay,
unique and
got it.
it is sortable. And it is just not key. We have one unique ID and you cannot make sense of it. It is key. I can make sense from the ID itself. That is what we'll try to do. Okay. The first is very simple. These are the four approaches that the author talks about and that we'll discuss. First is master application. Second is using the UUID system. Third is ticket server. And fourth is Twitter's own Snowflake approach, what Twitter actually does. Fair enough? First is very simple, master slave. As you can see, multiple people can query your web server or backend. All you do is you use a simple auto increment feature of MySQL or let's say whatever you're using, and instead of increasing it by one, you simply increase it by k, and k is the number of servers. That's it. It's very simple. We are creating a system for distributed system. That means multiple servers will be there. Correct. And multiple servers are, let's say, you're getting hit on multiple servers. So what should happen? Is you simply increment by k, which is number of servers that you have. Very simple approach, nothing special, but it has some scalability issues. Issues are it is hard to scale when there are multiple data centers. You continuously need to update your information. Um, and it is not necessary because if you are hitting one server and you're getting the request back, the problem will be what happens when you're adding and removing things. Okay? Especially when you're removing things. What happens to the existing IDs? All those kind of consistency mismatch will be there. So it is simple approach, but it doesn't scale as simple as that. Any questions here, Harsh?
No.
You know? It solves for scalability, but it doesn't actually scales in a real world system. Just about that. Then there is UI.
Like it is also limited by number of servers we are assuming. Like,
Yes.
yeah.
Okay. Then there is UID, which is number two. It is again a very unique, simple way. This is an algorithm which is very worldwide proven. Generating UID. It is a 128-bit number uniquely identify various things, and you can use it in various shape and form. And it has very rare capacity for collision. The UID algorithm. From Wikipedia, it says after generating 1 billion UIDs every second uh, for approximately 100 years, there will be a possibility of creating a single duplicate will reach 50%. It's for the length of 128 bit, if you keep running the algorithm for these much of time, then there's a probability of 50% that you will create one duplicate. Okay, so even though it seems very simple, as you can see, UID is very simple, just alphanumeric, and it's very simple alphanumeric, let's say identifier, and probability is very low for two unique ID, and so this means these are disjoint. Two requests have no relation. You simply generate a UID and there is no input needed. You will simply get a unique identifier. Okay, no timestamp, nothing. It doesn't matter. You can use it in whatever shape and form. Some of the people how they have used it, UID is like this. So there are various web servers and they all have their independent ID generators. Okay, so n servers will have n ID generators because the probability is so low. It's okay. That is the rationale. That is the rationale that it is so low that it's very hard for to create a collision. Hence, it makes sense. Okay. A couple of pros and cons. First is, for pros is very simple. Generating UID is very simple. You just don't need any input. Right? There's no need to create any coordination between server. Hey, you might intervene and generate the same ID, and synchronization issues between servers is very less because the probability of collision is absolutely goddamn very small. Okay, and it is very easy to scale because you don't need to worry about if you add or remove a server. Uh, every server has its own copy of generating identifier. Hence, no server has relation with anything else. So it's very easy to scale because it's just one copy with one server. Couple of cons for UID system is, first is it is 128-bit long. It's a little cover double the size that you were targeting at earlier. The 64-bit is okay, and 128 is a little long. You know? And it doesn't goes up with time. That means you just cannot use UID for any, let's say, sorting or making sense in terms of timestamp. Okay, hey, when was this information generated? There is no information embedded in that identifier, and it is not alphanumeric. Alphanumeric, I don't think is that big a con if you are able to abstract out the information. But for me, two that it doesn't scales in terms of time was the rate limiter. Okay, hey, there are limitations to UID system. Fair enough. Any questions on for UID till now?
Right. Anupam, just one question, not related to the method, just regarding the system that you are designing. So I'm just thinking like posts that you had mentioned, right? Twitter post and things like that. So we don't want that the IDs would be conflicting, right? But let's
Correct.
suppose if there are different scenarios for post and let's suppose comment. So those can contradict. So we are designing a system where for a specific use case, the ID should be different. Like there could be multiple SQL servers, multiple writes that would be happening, and we need that both of those databases generating different IDs, right? That is the problem statement that we are working on right now, right? Just
Problem statement is you want to store some data. You want to create some data. Hence, you need a identifier for it. It's okay to scale and various algorithm scales on a single server. What happens in a large scale distributed system?
got it.
The problems around it. That is what we're trying to teach. All of these algorithm works, okay, in some shape and form. It's more about what we are actually looking for and what are the limitations, just knowing about them so that we can pick and choose better. So next time when you will use a distributed system, you'll know, acha, so I have these many containers for my service. Every container will have its own ID generator and they will have their own unique ID. So if it's just a matter of me storing this in memory or something for a short term, it's okay because collision will happen once in a billion years, and I believe my system will not be that long. Okay? It is more about understanding that. But if you use the simple master application system, then you'll know, okay, hey, what happens if I containers are doubled? What happens when containers are taken down? In all those border scenarios, this system is likely to break. Okay? It's more about understanding the pros and cons of, let's say, or various approaches.
Got it.
Fair enough. So these are the two classic approaches that I believe you already knew. These are a couple of new ones for me also. So let's have a look at them. Ticket service is just very simple. It's just a one centralized server to create IDs. That's it. It's nothing new. Here you have distributed ID generation. This is again a centralized ticket server. There are companies who have created this. It's just that it is an auto increment server. It increments your let's say ID by one, but it is decentralized, even in a distributed network. Fair enough? So whenever you create, let's say, imagine in terms of containers, you receive the request, let's say for one company to create a request. Okay. After that is receive on our core request container. That core request container will make another call. Hey, I want a unique ID for request ID. Currently, we do it through MongoDB, right? Let's say that doesn't happen. The separate server which is running, ID generator server, and we can call it ID ticket server. You need to make a call to that server, and that server will return the exact value. Why do we do this? What are the pros? It is one, there are numeric IDs. First, there are incremental, there are sortable, all the classic different, there are small, so everything is served. Okay, and it is easy to implement also because it's just one server and it has very simple algorithm. Okay, whenever I get a hit, simply increment the existing counter by one and return it. That's it. Very easy to implement. Correct. What are the cons? There are cons. Very simple con. It is a single point of failure now. If your central system of one ticket server goes down, everything in the system goes down in terms of creating new things. Okay? That is it is biggest one, and one of and that is I believe is good enough for to not to use it in multiple. People don't use it. Fair enough. Now
Uh,
this is the learning. Anything on ticket
yeah.
server?
So, I mean, it is a central place, but can we sort of modify this to have a replica in place or a slave in place in case to counter this single point of failure? So, in case ticket server goes down, then we
People will do that. I'm not saying people. That is one thing that you will do obviously.
yeah
It's just that it's a single point of failure, and if you're okay with that cost, it's okay. People do use it. People do use ticket server. It's not like these things came out of thin air. People do use ticket server. The only con is if you are able to stake, like we have our core systems, right?
yeah
It can be part of our core system. Hey, our ticket server is down. It's acceptable for entire company to be down. It's just a matter of choice. It's as simple as that. It's not nothing wrong with ticket server. Ticket server scales well. People use it in decent amount of large scale systems. It's just about you want to pay that price. If it's okay, you go ahead. If you don't, you don't opt for it.
got it.
Enough.
Cool.
Now
So
we'll look at
one
go
more
ahead.
con, one more con can be there, right? Latency can also be a con.
Yes, but latency can be very low, less than 10 ms, 20 ms maximum. But that is an additional cost for every single request. That I understand.
Got it.
Hence I said key again simply add latency cost.
Got it.
Check latency cost, which is there. Now let's look at something which is interesting and what Twitter has done for their databases. So Twitter has said that divide and conquer is our friend cuff British rules, and so instead of generating IDs directly, we simply divide it into different sections. Classic British. And I'm very sure somebody from Britain came and talked to Twitter. Hey, this is how you solve your unique ID problem. Just divide them. See, so this is what they have done. The first bit is very simple. First bit is signed bit, 0 and 1. Okay, this is again a 64-bit system only. For 41 bits, they have kept it for timestamps. Okay, that is the second section. Third center is the data center ID, where it is running on. Okay. Fourth is the machine on the data center ID. What is the machine ID that you're running on? Fair enough. And the last is sequence number. Okay, and this is unique, and it is simply auto incremented by one, as simple as that. And it is so I'll repeat. First is sign bit. It will always be 0. So by design, Twitter has for now kept it as 0, so that they can simply multiply it by 2 whenever whatever reason they hit the limit. We'll talk about that also. Okay. This is simply saved to keep. Let's say they have some billion trillion combinations through this 2 to the power of 63 minus 1. That is the combination that they have, which is decent amount. Once they hit that number, they can simply split the first bit and they'll double it. Correct? That is their solution. And it can also be used to distinguish it between signed and unsigned numbers, but I don't think so. Positive and negative use cases actually there for unique IDs and database. Second is timestamp. Timestamp, they simply use epoch time. In case you remember what is epoch time is simply incremental time which is measured in milliseconds. It has started on 1st June, might be 1st January 1970. right? June or July or January.
I think
Epoch
it's January.
time. Huh, start. It's, I guess it's start. 1st January. It is 1970, 1st January. It is the time which has passed in millisecond. Second is data center ID. Let's say for them, this is how you can debug. So this is author did this by simply saying that they have saved 5 bits. So they can maximum have 32 data centers because to the power 5, correct? And they have 5 bits per machine. For every data center, they can maximum have 32 data centers, correct? Simple. This is unique identifier. Then there is sequence number, which is 12 bits, and this is the actual the uniqueness of it. Correct. Timestamp can be same across various data centers machine, and this is the uniqueness. But this is unique for that particular machine. Understand that also. Hence, you just cannot replicate it. You have created a unique identifier to reach that machine, and then you increment it by one every single second. See, this is very simple. Sounds very simple, right? And scales well also. It scales well at Twitter scale also. Timestamp is obviously the one of the most important ways because because this is how you abstract and solve for sorting and incrementality also. Correct? And the entire string is also alphanumeric. Sorry, numeric only. The entire string is the entire identifier is also numeric. As you can see, the timestamp from timestamp you can deduct. You can simply convert timestamp to decimal. Then you can see whatever what is the epoch time that you are getting, and you convert the epoch time into UTC, and you get the exact time. So when was this request created? Right? That is the identifier that you get. And this is something I also learned just by playing with the numbers. Epoch times ranges if it is of 41 bits. This gives you 2 to the power 41 minus 1 milliseconds, correct? That means after 69 years, the current system across the world, which started from 1970, they will, if anybody is dependent on timestamp, it will fail because epoch time will reach its limit. So if I do the simple math from 1970 and 69, that means some system will fail, are about to fail on 1st Jan of 2039. So let's see if that becomes an event in future. In case you guys don't know, because I was also very small guy, there was a lot of companies failed because they didn't handle the millennium time. If you remember, right? They didn't have any system to take care of 2000 or what to do. And same will happen when people are overly reliant currently on epoch time, and it will hit its limit soon, in not very soon, in next 16 years. So after 16 years, this might be a rational, oh, okay, let's migrate to some new system across the world. You'll hear, and I hope if you're all also working in tech. And Antariksh, I don't know, Antariksh might just fly away. Okay. So this is very system from a simple system from Twitter. Sequence number is very simple. It gives you 2 to the power 12 combination. This is 0 1 identifier, and it is simply incremented by 1, and that's it. So this is, in theory, this is the rate that you get, 4,296 new IDs per millisecond. This is the rate Twitter has. So that's about it. This is all I
So,
had for. Bola.
sorry. Doesn't this have a security issue? I mean, if the IDs are kind of incremental, then I know the epoch time, so I can just put the epoch time, put a random machine and get some.
So this is obviously Twitter will not expose everything to public, right? This is
So
what they
this is
have.
a hash that, but
They
this
can
is a
maybe
hash
hash it also.
algorithm that they are relying on just by keeping their hash algorithm, a simple hash algorithm to them. Matlab, if somebody knows this, then their whole system can fail and there can be a huge security issue.
Obviously, they're not exposing if they're hashing it out, just adding one more bit on top of it and something a very unique identifier that they're not telling anyone. This is Twitter. Twitter. This is simply Twitter Snowflake ID.
Mm-hmm.
So when they announced, okay, they notified what is the problem with. This is the article. If you see whatever we talked about is exactly this only.
Mm-hmm. Got it.
Exactly. So when they came up with Snowflake, the limitation of MySQL to not scale was one. This is the good question. It still uses Snowflake ID for everything. So they call it Snowflake IDs. Everything for post, direct message, user list, everything, comments, everything.
For tweets, matlab, I'm thinking ki if I just have an epoch time, I can find out all the tweets for that epoch time. Is that correct? Or I'm thinking something.
नहीं मतलब यहाँ पर ये लेयर भी है ना कि ये आइडेंटिफायर इसके ऊपर हैश लगा रखा हुआ उन्होंने इंडिपेंडेंट हैश भी तो लगा सकते हैं पांच सेक्शन पे they can have independent 5 seconds independently also now. We don't know how they're doing it. Nobody knows. It's not a public
Got it.
information. So uh, we can see
Hmm.
check secure key.
इसकी भी limitation है ना in terms of the operations that can be carried out on a machine. मतलब in the sense कि
इसकी लिमिटेशन ये है ना कि मतलब in terms of operation लास्ट सीक्वेंस नंबर कितने यूनिक जनरेट हो सकते हैं.
yep.
ठीक है तो यूनिक ये बाकी सब तो स्टैंडर्ड है. एवरीथिंग एल्स इज फिक्स्ड टाइम विल इंक्रीमेंट. ओनली सीक्वेंस नंबर इज व्हाट यू हैव इन योर कंट्रोल. In
Right.
terms of operation, every machine independently can handle 4096 operation every single millisecond.
Yep.
Currently, I believe it is okay. Twitter, even Twitter hasn't scaled to that scale. To imagine 4096 in every millisecond, so millisecond, second to second, second
तो
converter. Let's say 10 की power 3 है ना. So 20
like काफी आ
2096 एक
41
दो
lakhs per second.
हाँ
around
मतलब देख
24 CR RPM
हाँ तो नहीं नहीं ज्यादा है एक्चुअली.
into 60 होगा ना.
हाँ नहीं मैंने तो सेकंड का निकाला इंटू 60 और हो गया.
हाँ 24 CR RPM.
हाँ तो 20 एट एवरी सिंगल मशीन.
हाँ
That's
every,
every
that's a lot.
every single machine. It is insane. I don't think so. Even Twitter will ever hit this scale. They have simply solved it so robust कि हाँ भाई algorithm, and this is the simple power of algorithm. Somebody just uniquely sat down and uh, identified this, and this is the skill that they have. Only if they cross 24 crore operations at every single machine at, at a minute, then only the system will go down.
But even if they do happen to cross, they just need to add a bit in secure
That's it.
sequence number ना. Then it will be
हाँ
solved.
सीक्वेंस नंबर में लास्ट में ऐड कर देंगे और पैरिटी क्रिएट कर देंगे तब कम. और for them it's just a matter of adding bit at the last.
Correct.
That's it. And just by adding one bit, your combination will scale from 8096 to, let's say I'll take a blanket 8000
Into 2 हो जाएगा ना.
into 2 हो जाएगा simply. हाँ तो it will simply scale to 48 crore. It's just insane. Just insane. Today, that's it I guess for the session today. Any questions from your side?
Nope.
We had to discuss one more thing. Let me. So in case you guys don't know, market trees are actually very heavily used, not only to from last session, which is from to bring back systems from complete failure, and it's actually heavily used in blockchain. So let's watch one short video on the same. Fair enough? Is this audible?
Yes. No.
It's not audible.
Centralized. The first is what we'll call Vansel, and I'm going to tell you about Merkle trees and how they enable the decentralized
Is
web.
it only me? I can't see the screen.
Screenshot.
Share screen.
Hi guys. Now I guess.
Hi, my name is Tara Vansel, and I'm going to tell you about Merkle trees and how they enable the decentralized web. So I want to start out by talking about two centralizing forces that affect how the web works. The first is what we'll call the server problem. So if you want to upload files to the web, you need to have a server, but most of us don't have servers lying around, and they're also sort of burdensome to manage. So typically we choose the more convenient option, which is a hosting service like YouTube or Medium. Now this is convenient, but what it results in is a lot of web content being concentrated on the infrastructure of a handful of providers. The second centralizing force relates to how we address content on the web. We currently use what's called a host-based addressing model. And what this means is that if I upload a video to YouTube, the URL for my video is tightly bound to the youtube.com origin. And if I ever want to move my video to Vimeo, for example, I need to get an entirely new URL. So there's a lot of friction involved in exercising choice between hosting providers. And most likely, once I've made my original choice, I'm probably going to stick with it. Now, luckily, both of these problems can be solved with a peer-to-peer system. And the first part of the solution I want to talk about is called content addressing. Content addressing is pretty much what it sounds like. It's generating an address for a piece of content based on the content's value. And we do this with the cryptographic hash function. A hash function is a one-way function that takes an input, like a file, and generates a fixed length output, typically 32 bytes. And it's important to know that a well-designed hash function guarantees with extremely high probability that no two inputs are ever going to generate the same output. So a hash is a unique identifier for a piece of content. So how does this help us solve the host-based addressing problem? Well, if a hash is a unique ID for a piece of content, that means we can also use it as an address for that piece of content. So at this point, if I want to move my video from YouTube to Vimeo, it can maintain the same address, no matter where it's being hosted.
Nice.
But we still haven't talked about how to reduce the burden of hosting files on the web. And we can also do this with a peer-to-peer network. We can take a data set, split it up into small chunks, and distribute it across a network of peers. And then those peers can share the responsibility of providing bandwidth and disk space. Now, this does make the responsibility a little bit more manageable, but there's something else really important that we need to consider, and that's trust. Participants in a peer-to-peer network are anonymous and untrusted, so it would be really risky to download a file from a peer without first verifying that it's the file that you actually asked for, and not something malicious. And this is where Merkle trees come in. A Merkle tree has some pretty unique properties that allows us to do efficient data verification across a network of peers. So what is a Merkle tree? It's a binary tree where the nodes store hashes instead of storing chunks of data. Hashes of what? Well, the leaf nodes store hashes of chunks of data, and the parent nodes are a little bit different. The parent nodes are the result of concatenating the left and right children and then applying the hash function to that result. But let's actually step through constructing a Merkle tree so we can see how this works. So we have 4 chunks of data, and we start out by determining the leaf nodes. We're simply going to apply the hash function to each chunk. From there, we'll determine the parent nodes. Let's look at A. So to do A, we concatenate the hash of 1 and the hash of 2, and apply the hash function to that result. And we'll do the same exact thing for B and its children. Finally, we do the same thing for C, the root node, concatenate A and B, and apply the hash function. So a root node has a special name in a Merkle tree. We call it the root hash. And as we'll see in a few moments, this actually plays a pretty important role in peer-to-peer networks. So let's look at an example. Let's compare 2 Merkle trees to see if they're equal. Remember that a Merkle tree is just a representation of a data set, so in effect what we're doing is comparing 2 data sets to see if they're equal. You'll notice that these trees have different root hashes, and you might be able to see why. It's because one of the leaf nodes in the tree on the right is different than the tree on the left. So as a result, its parent node is different, and consequently that node's parent is going to be different as well. So a change in any single leaf node bubbles up all the way to the top, to the root hash. And this means that the only thing we need to consider when comparing 2 Merkle trees for equality is the root hash. And this is wonderful, because not only does it reduce the number of comparisons we need to do, most importantly, if we're doing this comparison over a network, then the only thing we need to send over the wire is the root hash. And typically that's 32 bytes. But how does this come into play when we start talking about peer-to-peer systems? Let's see another example. So I mentioned that the root hash has a special role, and the first value it provides as serving as an address for a set of files or data. And this is a lot like how URLs work on the web. A URL points to a set of files that live on a server somewhere, and if you visit the URL, you can download the files. But you would never visit a link from someone you don't trust because it might just point to a virus. And we have to apply that same principle here. When we get a root hash, it needs to come from someone we trust. So that's what we've done. We got the root hash C from a friend, and at this point, we can start asking peers on the network to send us the files that are associated with that root hash. And we got the files. We have 4 chunks of data, the numbers 1 through 4. But remember that it came from a bunch of random people on the networks, and we don't trust them, so we need to verify the data. So let's ask ourselves, how might we do that? Well, this is the second role that the root hash plays. We have the root hash from our friend, so why don't we just reconstruct the Merkle tree to get another root hash and see what we get? And that's exactly what we can do. We'll construct the Merkle tree with the data we receive from the network until we get a root hash, and we see that it's the root hash that we got as our friend. So we know with 100% certainty at this point that the data we received wasn't accidentally corrupted or intentionally tampered with. Because if it were, we would have gotten a different root hash. So at this point, you might wonder, if the purpose of the root hash is to let us address a set of content and to also do some integrity checking over that content, why don't we just concatenate all the data together and then apply the hash function to that? Why bother with a tree at all? And that's a pretty astute observation. That would work, but it turns out there is some value in constructing a tree, and we're going to see why in a second. So in the last example, we needed to download all of the data before we could verify it. But on a peer-to-peer network, we download data from people all over the world and at different times. So it would be convenient if we could verify data as we receive it. Likewise, we might not be interested in the entire data set. Maybe we only need 1 or 2 files. So being able to partially verify data sets would be pretty cool. And it turns out we can do that, and that's why we need to construct a tree. So let's see another example that's pretty similar to last time. We received a root hash from someone we trust, and we've started asking peers on the network to send us data. And we got the first chunk of data. It's the number 4. So let's ask ourselves, what other data do we need to reconstruct this root hash and verify that the number 4 belongs in this Merkle tree? Well, it turns out it's not very much data at all. We already have the number 4, so we can determine the hash of 4. We'll need the hash of 3 so that we can calculate B. And finally, we'll need the node A so that we can calculate the root hash. And again, we see that we got the root hash that we expected to, so we know that indeed the number 4 belongs in this tree. Now, it's really important to notice that the only thing we needed to download from someone we trust was the root hash. The data itself and all of the proof required to verify the data came from an untrusted peer. And this is a critical piece of making it possible to distribute the responsibility of hosting files across the network of peers. Merkle trees are used in dozens of projects, and they actually have some other cool properties that I won't have time to discuss today. But they're of vital importance to peer-to-peer networks and decentralized systems. Being able to address content with the root hash means that we get consistent links that stay the same no matter where the content is hosted. And being able to efficiently verify data sets makes it possible to distribute the responsibility of hosting files. In summary, Merkle trees make it possible for the web to be built on the small contributions of many rather than the concentrated resources of a few. Thanks.
So interesting learning about Muggle tree, as you can guess. Now you can guess कि DC++ कैसे काम करता है अगर सिक्योर होता तो, या फिर torrent कैसे चलता है, torrent से फाइल डाउनलोड होती कैसी है, and how they are able to manage this algorithm, and then actually expand it to blockchain also. And I was not able to read. I'll cover in next session also. Muggle tree are also used. What happens if your entire system is down in a distributed system? How do you take it back up? That is also where Muggle trees are used. So I'll cover that in next session. Fair enough. Cool team. Anything else from anybody else? No. I guess that's it for today. Thanks for tuning in. Okay.